So, ladies and gentlemen, this is presented here. My name is Dusan Krokavec. I am from East Slovakia, town Košice, from Technical University, Department of Cybernetics and Artificial Intelligence. Anything about me can be found on this my public web. What is presentation content, which I will try to take very short. It is at first it is present the ideas that connect the plan, the representation with ostensible Metzler system matrices, especially the system, for example, model of engine for F-18 aircraft of US airport to the theory of strictly Metzler and positive system. The second point to illustrate how this can be used in closed loop and state observer synthesis to get the idea of practical formulation by setting the parametric constants inequalities when solving by LMI solvers, and to make an illustrative example with some concluding remarks. The basic literature concerning the application model in this field is given on this literature. Uh, when I start, it's necessary to say I usually repeat this, that a professor is a man who likes to speak to sleeping people. So I would try to get up you and anything say about the continuous time linear Metzler system. What is the problem? The problem is that many systems are positive. That means that we have a non-negative initial states on the system. The output and state system has to be every time non-negative. And such systems are specific with this, that the system matrix A has to be Metzler. What means that Metzler system matrices are occurs in such system. It means that A is strictly Metzler if its diagonal elements are negative and all off-diagonal elements are positive. A is purely Metzler if its diagonal elements are negative and its non-diagonal are non-negative. Usually, this purely Metzler are occurring in the system which we know this is a compartmental model in economy and other systems. But in technical system, we such usually have no structure, and ostensible Metzler system are usually exist, and this means that matrix A is ostensible Metzler if its diagonal elements are negative. Minimally one of diagonal elements is negative, whilst the number of positive of diagonal elements is prevalent. This is the main problem of ostensible systems because it is not strictly positive. That means this implies from this Metzler structure. Basic problem with mathematical description. The first is that only inverse of a positive definite diagonal matrix is positive definite diagonal matrix. All other inverse matrix is signum indefinite element. So in positive system, it necessarily use the positive definite diagonal matrix variables. And such term for stabilization is used, the diagonal stabilization of positive system. The second are that we have an open loop with definite by matrix, which is strictly positive or not strictly positive method. Feedback has to be negative. and this feedback cannot destroy the positivity of the system. So we have a limitation by elements uh, closed loop system matrix now in this case, and this constraint are generally n squared because this is a square matrix of dimension n by n. So the uh, uh, minimal numbers of matrix inequalities which we can prescribe the constraints on the Metzler system, positive system in n. We use the n diagonal matrices. And the third problem is practical usually when I try to uh, use the linear matrix inequality toolbox for stability condition and linear programming toolbox for constraint description. But we prefer toolbox Sedumi package, which give the possibility to form also matrix equality in the design task. Modification applied from purely ostensible Metzler. The first means that if we have purely Metzler, the couple of parameters A, B input in the synthesis of controller, or couple AC instead of cellular synthesis must be taken, and because some of the elements can be off-diagonal elements can be zero, a structure, positive and definitive diagonal matrix variables have to be used. It is possible to usually be done only ad hoc for the given specific case. And maybe solution may not also exist. And working with ostensible system matrices, it is principal to find a matrix representation of this form, constructing an entry-wise negative and Hurwitz matrix AM, and with prescribed stability, and the strictly Metzler AP, which it is minus a P as a plus construction. This idea was presented in our papers. The last from Ostensible Metzler was in last year in the control conference in Portuguese. How to work with diagonal parametrization? It means replacing a square matrix A by its rhombic form, where the row, every row is shifted circularly, and we obtain this rhombic representation. And diagonals of this rhombic representation prescribe the parameter constraint. It is evident that main diagonal is this matrix, and this must be negative, definitely, and all other diagonals which we constrain rhombics has to be positive, definitely. This is specific for the controller task. And how to explain it more in detail, the basic closed loop system description is given by this relation where the A minus BK is closed loop system matrix C. State feedback is negative. B has to be non-negative and K has to be positive. So we, in the face of possibility that negative feedback destroyed the Metzler matrix structure, and destroying the Metzler matrix structure means the positivity of the closed system will fall. How to work with this? It is simple. parameters this matrix AC by this way, where A theta are taken from rhombic representation, and uh, uh, every row of gain matrix K is explained in its diagonal form, and every column of input matrix B is also described by its diagonal, and all is connected with circular shift matrix L. More detail for be presented in the example. This is controller. When we work with state observers, especially for system which, for example, for detection, the observer is used uh, as a base for residual fault generation. The rhombic construction is represented by circular shift of columns. Here is this uh, permutation circular matrix. And now also the diagonals of this rhombic representation can be used to prescribe the parametric constraint on the observer closed loop system matrix. So we can see that it can be formulated as a dual task. Now we have observer dynamics described by this relation, and A theta are taken from rhombic representation, and now the unknown matrix J has to be parameterized as a diagonal for every column of J, and matrix C has been represented by diagonals for every row of matrix C. And we have another parameterization for system with observer system matrix. So we can say here that this is dual representation. When we transpose the matrix AE of observer, we obtain this relation that it is necessary to have algorithms to design only for controller, and using the dual form, we can obtain the solution for observer. How to formulate the task when we can design a H infinity control of strictly Metzler system? What it means that we have a disturbance acting on the system, and infinity norm means that we try to minimize the impact of unknown input disturbance on the system output. This norm, or this upper bound of this norm, is given by the parameter gamma, and it's possible to tune in design gamma is be as small as possible. And we can say that closed loop system matrix AC will be strictly Metzler and Hurwitz. If for given strictly Metzler matrix of open loop A and non-negative matrix B, C, D, there exists positive and definite diagonal matrices Q and RK, and a positive scalar gamma, such this set of matrix inequalities is satisfied. We say that these three inequalities, this is matrix variables used in the synthesis of the controller. This set of matrix inequalities means the parametric constraint to have in final results that also closed loop system matrix will be Metzler. And this big inequality is nothing else than the Lyapunov, generalized Lyapunov matrix inequality guarantee the closed loop system will be stable. We say that this solution with quadratic stability, not with asymptotic, because we have a norm bounded disturbance satisfying condition from the positivity of the system. And when we obtain that this set of inequalities is feasible, we can construct the matrix K by every its row. What is the problem with matrix A is not strictly Metzler, but is purely Metzler. This theorem is formulated for the case that only a zero element AGL of the purely Metzler systematics is uh, zero. Then exists solution if we have obtained positive and definite diagonal matrix Q, and at first positive and definite diagonal matrix RK, if the non-negative B elements are zero, or semi-positive and definite diagonal matrices RK, if the non-negative B the elements are not equal to zero. And we can see that is approximately the same like before. This is matrix inequality guarantees the system will be Metzler. This is Lyapunov inequality guarantee that system will be stable, and these are matrix variables. And specifically, it is here that RK in a positive definite diagonal matrix, and in other case, in this position has to be zero. This is structured matrix inequality, and this position has to be zero, and this means the result is a positive semi-definite matrix of this. Also, the solution is approximately as above, but in the first case, we have a strictly positive matrix K, and in the second case, we have only non-negative matrix K. What is ostensible Metzler system? As I usually say that it is a complicated, approximately or large nonlinear system like the fourth engine for airplane. Description is standard. But the problem is that we have A is ostensible Metzler matrix, and the minor idea is decoupling the ostensible system matrix A so that A is equal to plus plus R minus, where R plus is strictly Metzler, R minus is element-wise negative and Horowitz. This idea we obtained from the time delay Metzler system, because there is exists the results system with time positive system with time delay mean state are independent on the value of time delay. So how to construct this matrix A minus? We formulate it in this way that R plus, or better, R minus is I minus circle minus PM given by this relation. And R the parameters of R minus is constructed from the matrix A plus or A minus. That means using this rule that the elements is non-zero in this matrix A if it is positive and zero if it is negative on this matrix in opposite side. It will be more illustrated in the numerical example for this. And parameterization of an observer system matrix, because this task is dual, we will continue with with the observer, because it means the specific application of Ostensible Metzler system. It is a standard Leuenberger observer. And defining this error between state of the system and observer state, we have this systematics A minus G multiplying by C. Uh, uh, the, this modifies the condition, substituting this here for A plus A minus 1, that we can only modify a P part, a plus part, to be strictly Metzler. And a R must to be given as a Hurwitz and stable. Design of this observer in the Ostensible Metzler mean that not matrix A, but only matrix A plus is taken for the rhombic representation. We obtain this matrices A theta P, and we obtain the condition for parametric constraints. These are matrix variables, and the Lyapunov matrix modified by these two elements, P plus P minus A minus transpose multiplying the P. And if this task is solvable, we can compute the giant matrix by the same. We have present it in this year in the IFRIC World Congress in Yokohama, which was last month. A representation for interval definite ostensible system. What means interval definite? When we identify the system, usually we cannot say that we have only one solution in parametrics, that we suppose that we have lower and upper bound of the system matrix A. And really, we don't know really what is the matrix A, but every time it must be covered by this inequality. And it means that we have to construct parameterization for a lower bound of matrix A for upper bound, and using this implementation by this relation where lambda 0 is the maximal value of the value with maximal real part, positive real part from the matrix A M minus 0. So when we have interval parameter description of system, we have to construct the observer for the lower and upper bound of the states. That means we use two Leuenberger observers. And it is necessary to design the first and second observer will be stable, but connected, that these two observers are connected by the same matrix J. This means connected by the same matrix variable in the design condition. And the task is also to construct I matrix AM for lower and upper lower bound and upper bound, and to construct design condition for plus for lower bound and plus for upper bound description. This is design condition. We can see that interval observer design is approximately the same, but only this is given for lower bound and this given for upper bound of parametric constraint, and this is extended design condition from for stability. This is expanded Lyapunov matrix inequality. We can see here that also we accept the lower bound of AM and an upper bound of AM. So what is the result? Result is that we use the Ostensible Metzler interval observer that this lower bound of interval state will be non-negative if A is less than if A is greater than lower bound of A, J and C are positive, and AP plus M must to be Metzler, must to be Hurwitz. This will be positive, this will be positive, and this also will be positive, and the system lower bound will be positive, that upper bound and other state estimation will be non-positive also too. We have presented this idea in the this year in the Frontiers in Aerospace Engineering Navigation Guidelines. It is 3 weeks. After that, the paper was presented, we have 80 reading of this paper. Very slowly example. It's better to see. We have this model of US Navy engine F404 of aircraft F-18. We can see that base is common, but it's not negative, non-negative. We have negative elements. But for observer, the matrix B is not substantial. Matrix C is non-negative. D is non-negative. And we have parameters that diagonal every row of C by this way. This is permutation matrix used in this design. Also, we can see that A lower and A upper satisfy the condition that lower 8 is element-wise less or equal the elements of upper A. And we have 2 negative elements. These are the same, but these are different. So we can construct a plus from these matrices equal, because positive elements are the same. And negative is for lower bound is given by this way. Only these 2 elements are negative, and upper bound, these 2 elements are negative. And when we use the parameter Ni is equal this value, we can construct IM circle. What is main idea? Main idea means that trace of a matrix means the summation of eigenvalue of the matrix. And since trace of this matrix is 0, it is evidently that we have positive and negative eigenvalue in the matrix A circle. This means this is unstable, because positive eigenvalue means that it is on the right side of the complex plane of S. So we obtain this spectrum of eigenvalue of law from upper bound given by this value, and we can see that maximal real eigenvalue is this. Also for upper bound, we can oh sorry, this is change. And we can that this is different maximal eigenvalue, positive eigenvalue, and so we can compensate it using it. When we use only lambda 0, we can see the system is on the limit of stability. But there is, I don't know now written this theorem that we have two matrices, and one is diagonal, so we can don't change the eigenvectors, but move the eigenvalues. So we add this parameter delta, this relation, so satisfying integration. And we can see that Rm lower and Rm upper are element-wise negative, but its eigenvalue are negative. These matrices are stable. And only part for positive composition projection is used to design a matrix plus by this way. We can see that these matrices are strictly Metzler. All elements on my diagonal are negative, and all elements on off diagonal elements are positive, and more over lower AP is element-wise less than upper. And using these matrices in the rhombic representation, we construct matrix A plus L1. But it is very simple. This is this one, and this one is this. And this is this one, and this one. And this one, the last is this one, and this one to construct the diagonal representation. Solving using Sadumi package, we can see the matrices matrix variable P, S1, and S2 are diagonal and strictly positive and definite. That implies that matrix J is strictly positive. And we guarantee that matrix AM is Hurwitz. So we can construct matrix AP for observer, and matrix AP all is also strictly Metzler. Oh, interesting is when we use the same J in the common description of the system, the position of in the matrix A where the negative element occurring are the same. We have on this position the negative elements, and looking here on this position we have negative elements. We simulate the result for the closed loop system. The input is given by this relation. The W is the gain of the desired output, and W T is desired output given by these two, by this steady state scalar vector, and disturbance is modeled by the Gaussian noise. This is initial case, but what is we can see here, for example, on this, that this is the upper bound of the state estimation. Red is the lower bound of the estimation, and the real state is between this upper, but also for the side variable. What say the conclusion? It necessarily said that linear system with ostensible system matrix are not positive. Only a part of the system state variable are positive. In this case, first and the third. Second, not. The worst is with incomplete positivity to work the system representation Rm plus Rp is proposed, constructing entry-wise negative and with Am, which describe a destability region and strictly Metzler A. Parameterization AP is necessary using rhombic diagonal representation respecting duality of the control of the task to prescribe structural constraints in the matrix inequalities. The stability is formulated by Lyapunov matrix inequality using diagonal matrix variables, reflecting diagonal stability principle. For interval ostensible Metzler system, different destability regions have to be defined to set this element-wise condition for upper and lower bound, forcing intervals on positive variables. It's necessary to say that we have used two parameters to satisfy this condition. The Darcy convex LMI problem resulted ostensible Metzler systematics by positive or non-negative matrix. Something with additional references. The first are mathematics background for Metzler system. This is Berman and Hershkovitz matrix stability of the implementation. Berman non-negative matrices in dynamical systems. Borutsky bond graph modeling in control for diagnostic prognosis. Distributed coordination approach to reconfigure control process design. Very interesting is book, Hada de Chalamoina, non-negative compartmental dynamical system. And then for the application, Mahmoud multi-agent system introduction and coordinate control. Maybe 1 minute. I already said that you will have a set of drones. It is impossible to control this set of drones in war application, for example. Driving all drones. We have to drive to control only the leader. And another can learn from this leader. But this learning has to be positive, not periodical damping. Because on the radar, you will see all drones which are, have to switch it, yes? And the operator now that it is not necessary to destroy these switched drones. It is necessary to destroy this leader, which not switch. This is the problem for. And the second problem are when we apply this idea for networking control system. This is the last, yes, this is the compartment with networks and neighborhood interval observer based control of multi-agent system distribution. And you don't obtain this Metzler structure of the local estimation of the state in the control. Every time it will be exponential periodical damping. So thank you for the attention. I think that I hope I don't destroy you like the leader of agents.